Okay, we're going to continue on here and talk about organic chemistry still. So last time we really got into alcohols. So remember that the functional group there of an alcohol is an OH group. And so when you do see that OH group, that is basically what's going to make it an alcohol. We name alcohols just like we name pretty much everything else. It is based off of like those first 10 alkane names. Remember though that we do need to, starting with about 3 or more sort of carbons, we do need to give the location of where the OH group is located. So again, if we had something like this, we would need to give the location of it. It would be based off of 3 carbons, which is propane, propanol, location of that OH group at carbon number 2. So that would be our 2-propanol. Remember that it is the OH group here that takes the priority. You want to give it the smallest number of, or there is just the smallest number, I suppose. You want to number the longest carbon chain to give that OH group the smallest number. Once you sort of lock in that numbering for the OH group, every other thing that may be attached there is numbered accordingly as well. We do have the way we make an alcohol, as we talked about, is you could very simply make an alcohol by doing a hydration reaction of an alkene. And again, hydration reaction means basically you're going to add water in this case. And remember that this is an addition reaction where basically our double bond becomes a single bond. And one carbon will get an OH group and one will get a hydrogen. And in this case, that is what's going to form our alcohol here as we go from an alkene to an alcohol. We can also go backwards by applying heat, and that's what's known as an elimination reaction, and that's a dehydration of an alcohol. Dehydration of alcohol basically means we take the water back off, and when we take the water back off, we do lay a double bond back in there between the 2 carbons where we would remove that water from, and that will obviously give us the guy on the left there. We could classify alcohols as primary, secondary, and tertiary based on the number of carbons that are attached to the carbon that has the OH group. So when we take a primary alcohol, like so maybe. And again, this is a primary alcohol. It will do an oxidation reaction, and that's sometimes symbolized with that little O. And that oxidation that we talked about is basically the loss of hydrogen. And remember that when we have an alcohol, the way that we lose the hydrogen is we always take one there from the OH, and we also take a hydrogen from the carbon that's attached to the OH. And that's going to give us the H2 that basically comes off, and that's basically your definition of oxidation. Remember, as we talked about, really nothing else changes in this case, so you could just pretty much copy what's there. And the one and only thing that changes is we do need to insert a double bond there between the carbon and the oxygen where we remove the hydrogen from. This gives us another organic group, which we'll talk about today, which are aldehydes in this case. By the way, if you actually oxidize this guy one more time, you will get what is known as a carboxylic acid. And actually, that is actually going to be an insertion of an oxygen here, basically, which is another definition of oxidation. And that makes this group right here, which is a carboxylic acid. So you could actually oxidize a primary alcohol twice. Once gives you the aldehyde, and then if you actually oxidize the aldehyde, you will get a carboxylic acid. We also talked about secondary alcohol, which will look maybe something like this. I'll do this guy, this guy. I'll do this, and I'll just draw it out like so. This is, again, a secondary alcohol because the carbon that has the OH group has 2 carbons attached to it. Once again, we can oxidize this guy. And by oxidizing this, we're again going to take always the hydrogen off of the O, always the hydrogen attached to that carbon. And once again, nothing else is going to change. So it's just going to look the same, basically. We'll have our oxygen up here. We will need to, again, make that into a double bond. And we will also have, obviously, our H2 that came off there as well. This creates what is known as a ketone in this case. And again, lastly, we talked about at the very end, a tertiary alcohol. And if you have a tertiary alcohol like this guy here, and you go for an oxidation, you are going to get no reaction going to occur, and that's because it does have the 1 hydrogen, but it is missing that second hydrogen there on the carbon, so it will not go through any type of oxidation reaction. Bless you. So since oxidation reduction always kind of occurs together, if you kind of do the opposite reaction starting over here, you could put the hydrogens back on, you get your primary secondary alcohol, and that's the reduction reaction occurring. And also on the primary one that we saw, you could also go back this way, and that is the reduction reaction. Again, basically putting the hydrogens back on over here gets you back your alcohol. So you can go either way, primary or secondary, oxidation, reduction. Again, oxidation, losing hydrogen, reduction, basically putting the hydrogen back on, going in the opposite direction. Any questions on that there? Okay. So we talked a little bit about some of these. Again, methanol is known as methyl alcohol. Again, it's used, as you can see, in paint strippers. And here we got our oxidation occurring, removing a hydrogen there and one of those hydrogens, giving us our aldehyde here. And again, if you oxidize an aldehyde one more time, you're actually just going to insert an oxygen there. And again, that is another definition of oxidation. And you'll get your carboxylic acid. A ketone will not do that because it's also missing that hydrogen on the carbon. So it won't be able to actually do that. Ethanol, as we talked about there, alcohol. Let's then talk about thiols. Thiols are sulfur containing groups. So the functional group of a thiol is the SH. So kind of like the alcohol, but it's a sulfur containing group, hence the skunk here, I assume. And because it contains sulfur, it doesn't smell so good. And as you can see here, here is our thiol group. These are found in cheese, onions, garlic, oysters. They also put sulfur in gas so you can know it's leaking, so you can actually smell it. Usually, natural gas has no smell unless they put that in there. In terms of naming thiols, you're not going to be responsible for that, so don't worry about it. That's good. Basically, you just put thiol at the end of it, basically, is what you do, but you don't have to worry about it. But in terms of thiols, though, you do need to know a couple reactions that do take place with it. And it's also sort of an oxidation reduction sort of reaction. So let's just say we had 2 thiols like this, CH3, CH2, CH2SH. And let's say we added it to this thiol here, we'll just make a small one. So when we do this and we take 2 thiols together, what happens is we are actually going to remove hydrogen. So we're going to actually remove hydrogen there, a hydrogen from each of the thiols, and that'll give us our H2. And then basically what happens is we're just going to basically squeeze the two things together. So we're going to remove the hydrogens, squeeze the two things together. So once again, as we've been talking about, you don't want to get super fancy with anything, but you're just going to copy this way and then connect it this way. So that is what I'm going to do. CH3, CH2, CH2, S to the S, and CH3. This makes right here a disulfide bond or a disulfide bridge, which sometimes you see in amino acids like cysteine, which has actually an SH group in it. It will make this disulfide bond or bridge. So when you put two thiols together, basically you're going to remove hydrogen, squish both ends together, basically. The connection is always this connection. So the connection always is the sulfur to sulfur connection to make that disulfide bond. So as you can see there, if I had something like this, why don't you take a moment here and draw what you would get. So why don't you draw the product of what you should get in this case? Okay, so let's take a look. So I personally, if I see two thiols going to come together, I personally like to kind of turn them around so they're facing each other. So I personally would maybe just kind of rearrange this guy here and turn it around. So kind of the sulfurs there are facing each other. And remember how many there were before I erased it. I hope that's the right number. Was that the right number? I hope. All right. So at this point, when I do that, now what I need to do is just take out the hydrogens. And when I take out the hydrogens, that's going to give me H2. And now I could just really copy it right from left to right here and put everybody together. And we'll do this. And again, the connection, always this connection here. You don't have to box it, but that is always connection. And was it 3 more carbons at the end here or just 2? It was 3. All right. And we'll end up with this right here, making our disulfide bond. So sometimes it's easier if you just kind of turn one so that the sulfurs are sort of facing each other, box out the hydrogens, and then just go left to right and put everybody together. Any questions on that there? Now, if you did have, let's just say one of these guys, and you wanted to break them apart. So clearly, to put them together, we take the hydrogen out. To break them apart, you need to put the hydrogen back in. So this is basically HH. So how do we do that? Well, it's always going to be broken apart right where it's put together. So that is where we're going to break it apart. And I would just at this point just draw the two parts. So you got this, you got that. Then on the other side, you got this. And what is left is, again, a hydrogen will go to each. So I'll make them a different color here. So this guy will get a hydrogen and this guy will get a hydrogen. So if you want to kind of make a disulfide bond, you're going to put two thiols together, take out the hydrogen. If you need to break a bond like that, you're going to throw the hydrogen back in and break it right there where the two sulfurs come together. Everybody gets a hydrogen. Any questions? I'll hold that there. All right, so for thiols, you need to know the functional group and those two reactions pretty much right there. Yes, putting it together and break it apart. Any questions on that one? Okay. Then let's talk about the next functional group of organic group here, which are ethers. So the functional group of an ether is this sort of run here, a carbon, oxygen, carbon run. So that is your functional group. And that is what you're looking for. So basically, there are a couple ways you can name ethers, but we're going to go with, I think, what they do in your book, which is more of a common name for ethers. So Why not roll, bless you, with a common name? So the way that we do a common name for ethers is pretty simple. We find the oxygen in the middle, and then we basically look at what's on the left and the right-hand side, or maybe even on top, of it as groups. So if we look over here, that is a 1-carbon group, which is a methyl. This is also a 1-carbon group, which is a methyl. That is 2 methyls in the same compound. That would give us dimethyl. And then simply we just put ether at the end. So dimethyl ether is sort of like the common name that you would name it. The IUPAC way, you actually put oxy in front of the group, and then the longest carbon chain, you just name like normal. So that would be methoxymethane would be the IUPAC way naming. And I think the common name is much, much better in this case. So you want to identify the oxygen and the 2 groups or groups that are attached there. So here, if we look at this again, we have our carbon, oxygen, carbon, which tells us it's an ether. We look at the oxygen to the left, we have 1 carbon group, which is a methyl group. To the right, we have a 3 carbon group, which is a propyl group, much like everything else that we name alphabetical order first. So methyl before propyl. So we go methyl, propyl, and again, we just put ether at the end of it. And that would be the common way of naming it and the way we'll do it in this class, which is methylpropyl ether. Any questions on that one there? Now, ethers obviously put you to sleep, all right? They block signals to the brain there of awareness. Over the years, they've sort of changed the ethers a little bit, made them a little bit less of volatile with side effects like flammable. They put a lot of fluorines in there as opposed to the hydrogens that were there. And again, changes some of the properties of it, makes it a little bit more user friendly, I guess is a way of saying that. Why don't we draw some of these guys here? So why don't you draw 3-pentanol, ethanol, diethyl ether. Why don't you also draw, let's do ethyl, propyl, ether. Why don't you name this guy as well? Okay, so let's take a look. And again, since we're drawing here on the left, we always want to work backwards. So remember, the name gives us some information. The first thing we should see is OL, which tells us it's a alcohol, right? And pentane part of it tells us it's 5 carbons. So just like normal, we'll lay up some 5 carbons here. We'll do a little condensed formula here. And OL means it is an alcohol, and that is where the OH group should be at carbon number 3. And once again, since you're drawing, I'm going to go left to right. Actually, in this case, it really doesn't matter whichever way you want to go. So I'm going to go there. Now, just like normal, everything else at this point is going to be hydrogens. Again, to get everybody to 4. So we'll need 3 there. We'll need 2 there. Just 1 here as it has 3 bonds. 2 and 3. Any questions on that one there? Next one is ethanol. Again, we see the OL tells us it's an alcohol. The ethane part tells us just 2 carbons. I like that. That doesn't seem like that too bad. In this case, there's no number, and that's really because we really don't start numbering alcohols until we get to 3. So this case, you could really put the OH on either one. It doesn't really matter. I'll go over here just for fun. Again, now at this point, we're just going to kind of hydrogen up everybody, and we're good at this point. Any question on that one there? All right, now we're into ethers. And since we're going kind of common name with ethers, we know for sure that it is a carbon-oxygen-carbon connection, right? I personally like to start with just the oxygen since that's in the middle, right? So I'm just going to start with an oxygen. And frankly, if you want, you could do each of these here. So I know diethyl ether. Diethyl means there's two ethyl groups, so one on each side of the oxygen. So at this point, if you're not sure, you could just do the carbons like we normally do. So 2 carbons there, 2 carbons there. And at this point, we could fill in our hydrogens. Same idea, we just want 4 bonds. So we'll go H3 here, we'll go H2 here, H2 here, and H3 there. Yeah. Any questions on that? Yeah. Say it one more time. The one I just drew is this one. Yeah. Is that what you're asking? Yeah. And that's what it means basically. So the ether part's right here. It's our carbon, oxygen, carbon, right? So that's the ether part of it. And again, when we're naming it, kind of common name, we're going to go to the oxygen. Again, we see our two carbon group there and our 2 carbon group there gives us our ethyls on both sides. Yeah. Ethyl propyl ether. Once again, I'm going to start with the oxygen in the middle. Ethyl means that it does have 2 carbons, and really same idea here. It doesn't really matter which side of the O you put it on, to be honest with you. So I'll go left. So I'm going to do just 2 carbons because that's basically the ethyl. Propyl is based off of propane, which is 3 carbons. So we'll go opposite side with that. And now at this point, we're just down to hydrogens to get to 4. So we'll do some 2s there and a 3 there. Yeah. Any questions on that one there? All right, so we do have some to name here. And again, we want to recognize what we're dealing with. So we should hopefully see that is a carbon, that is an oxygen, and that is a carbon. So that is your ethyl group there, your ether group, not your ethyl, but that's your ether group right there. So once it is the ether, we know we're going to kind of go common name on it, and that's going to be the end of the name, right, which is ether. Now what we have to identify is really what the groups are to the left and the right. So if we go to the right here, that's 1 carbon and 2 carbons. So that is an ethyl group. Going to the left, that is 1 carbon, 2 carbons, 3 carbons, 4 carbons. That is a butyl group, I believe. And again, we're going to go alphabetical. So B before E. And that's going to be butyl, ethyl, ether in this case. Any questions on that one there? Lastly, we got an OH there. So that makes me think alcohol. So we want the longest chain that contains the OH, right? So although I started writing here, we got 1 carbon there, 2 carbons, 3 carbons, 4 carbons, 5 carbons, 6 carbons, and 7 carbons. So 7 carbons is based off of heptane. That's now going to be heptanol, OL. We do need to give the location of where our OH group is located. If I go left to right, 1, 2, 3, 4, 5, 6, and 7. If I go right to left, we'll call it the red numbering. That is 1, 2, 3, 4, 5, 6, 7. Now, in terms of the OH in this case, right, it does not make a difference which way you go. That OH is going to hit carbon number 4. That means this is 4-heptanol because of that. Now, as we talked about, I think last time, we do have a chloral group here. Now, it kind of does make a difference now, maybe which way you would want to go. I would most likely want to go which direction here? Yeah, the red direction, because that's going to actually give that group the smaller number, right? So it's going to give it a 2 versus a 6. So this will be a 2-chloral 4-heptanol. Any questions on that there? Yeah.
Out of curiosity, in terms of naming it, so like say for the butyl ether ether, would we, I'm not sure if it would matter, like at least for me, it makes sense at least to kind of like where I'm writing it for the butyl and the ethyl to have a capital B, a capital E, and a capital E for the ether. I know it's just like semantics with that.
I would probably be okay with it. Usually, I'll be honest with you, usually it's lowercase for all of them, but you know, it's okay for me. Yeah. Other questions? Yeah, so usually probably don't capitalize too much of these things. You would kind of go lowercase on most things, but it should be okay. Other questions? Yep. All right. Yeah. Mhm. Yeah. Mhm. All right. So let's talk a little bit about some properties of alcohols. Obviously, an alcohol containing sanitizer, 60% by volume or 85% by volume there. We got a little isopropyl alcohol in there. Alcohols, as we talked about, again, can be classified as primary, secondary, or tertiary. And as we saw, it is important in terms of reactions and what you do get out of them as to whether or not you'll get sort of an aldehyde, a ketone, or you'll get no reaction. So we want to classify each of these. So why don't you take a moment for each of these and determine, are they primary, secondary, or tertiary alcohols? And while we're at it, why don't you also draw the product you would get if I oxidize each of these? A little good practice, I suppose they call that. All right, so name it and then also draw the product of the oxidation of each of these. Okay, let's take a look and see. We'll start with the naming. So clearly here we got some alcohols. Maybe we didn't talk about naming. Primary, secondary, or tertiary here. So first one is what type of alcohol? It is a secondary alcohol. Again, this is the carbon that has the OH group, and directly attached to it is two other carbons. So that makes it a secondary alcohol. By the way, the name of this guy, 1, 2, 3, 4 carbons. And on carbon number 2 there, so 2-butanol in this case, right? Now, looking at the next one, primary, secondary, tertiary, this is a primary, as that is the carbon that has the OH. It is directly attached to one other carbon. That's going to be a primary. This is 1, 2, 3 carbons, which is propanol. And again, the OH is actually on carbon number 1 here, as you do need it because you could have 2 propanol, which would be different in this case. Lastly, this is going to be our carbon that's attached, and it's attached to 1, 2, and 3 other carbons directly. That makes it a tertiary alcohol. The name of this guy looks like 1, 2, 3, 4, 5 carbons, which is pentanol. OH group is at carbon number 3, which is 3-pentanol. We also have, by the way, one more methyl group hanging out there, also at carbon number 3. I'll go above it, 3-methyl, 3-pentanol in this case. Any questions first off on the classification or the names here? All right, so the added on here is, let's do a little reaction products here. So remember, oxidation pretty much for alcohols means we're going to remove hydrogen. So as we talked about here, maybe I'll kind of clean it up a little bit here so kind of see everything. What we're going to always look at when we're removing this hydrogen is it should always come from basically the hydrogen that's attached directly to the OH or the oxygen. And then the other hydrogen should come from the carbon that's attached to the oxygen. And those are the two that basically should go away. And at that point, we would have obviously H2 pop off of it. Once again, nothing's going to change. So I'm just going to draw, like I said before, exactly what's there, except obviously in this case, I'm taking out the 2 hydrogens. And the other thing that we always do in this case is when we remove the 2 hydrogens, where we removed them, we got to insert the double bond. Otherwise, we're short bonds, basically, right? And there we go. That again goes from a alcohol to a ketone, as it is a secondary alcohol we started with. Question on that one there. Looking at the next one, our primary, same deal. Going to oxidize it. H from the O. I'm sorry, yeah. Can you put the H2 back? You absolutely can. And it would go in the other. Are you asking in terms of like how it's written? Can you draw the picture first and then write plus H2? Is that what you're asking? Yeah, it's perfectly fine. As long as both of those things are on the right-hand side of the arrow. Yeah. Yeah. Other question? Okay. On this one, we got the H off of the oxygen. And then in this case, we're actually just going to take one of those, obviously not both of them. So we're just going to take one of those. And that is going to give us, once again, the H2 that will come off. And this is going to be pretty much the same. We do have to be careful here because we did not remove both of those hydrogens on this last carbon. So I'll just draw it out. We still have a hydrogen there, and we also have that oxygen sort of connected to it as well. And once again, we need to insert our double bond between the carbon and the oxygen always in this particular case. Perfectly fine if you drew the double bond to the right, if that's a question. So perfectly fine if you did this. That's okay too, technically speaking. That is basically what's going to happen. But sometimes people draw it out so you can kind of see the aldehyde group here that looks like that. Question on that there. Also remember that even though you may draw it like this, the connection here is this connection here between the carbon and the oxygen. And again, that hydrogen is connected to the guy on the right. Lastly here, this is our tertiary alcohol, which means no oxidation here. And again, no oxidation because we are missing that second hydrogen needed on that carbon right there. We have the first one on the oxygen, but we don't have the second one that's needed for that reaction to take place. Any questions on any of those there? Yeah. All right, so let's talk a little bit about solubility with alcohols. Alcohols are polar because they do contain that OH group. So because alcohols have this, that is a polar group like we talked about with bonding. The oxygen is more electronegative and the hydrogen is less electronegative. So it creates that really polar bond. And that works really well for alcohols and water because water pretty much is that bond on both sides. And it is more negative on the oxygen, more positive on the hydrogens. And that's what makes, say, alcohols, for example, like methanol here, really soluble in water because they could hydrogen bond with each other. That is usually the answer for any question of why is this soluble and why does it have like a high melting point, boiling point, because it has the ability to hydrogen bond is usually the answer there. Hydrogen bonding, again, is an intermolecular force. It's a relatively strong force, but it also makes something like methanol really soluble in water because water will hydrogen bond with itself, which means when it goes to interact with methanol, it's going to do that like dissolves like. So they're going to use the same type of forces and going to make them mix really, really well. So a couple of things happen with alcohols. They're very soluble in water, but the solubility does start to decrease again around 5-ish carbons or more. So when you start building out like we see down here, a lot of carbons, which is the non-polar part really of this molecule, it gets in the way. And again, sometimes referred to as steric hindrance. It's just this big non-polar part that's in the way. And it gets in the way of this little OH group here being able to interact well with water. And it makes it pretty much insoluble in water. It's also relatively large, which makes it also not really great to fit in with water, which is a really small molecule. So if you think about if you want to dissolve something in water, the water molecules themselves are attached to each other and they're relatively small. So if you want something to dissolve in water, you have to get rid of some water interactions and replace them with something that's very similar. And as we start building out a lot more carbons, it gets really big. It doesn't have places to interact well with water, and we see the solubility really start to drop a lot. So as we can see here, once you hit about that 5 or more carbons, we're going to really see the solubility of these alcohols start to drop. By the contrast to that is if you had a alcohol that had multiple OH groups, you would actually see the solubility increase. So if it's something with a lot of OH groups on it, That's going to help with solubility in things like water, because everywhere there's an OH group, there's a place for it to interact well with water. So it's going to interact really, really well. So that's sort of the opposite of it. So you could almost sometimes counteract all these carbons if you actually had more OH groups on it. For example, something like sugar, which is a relatively large molecule, but it's littered with a bunch of OH groups all over it. And again, that's what allows it to be relatively soluble, obviously, and sugar will dissolve in water pretty easily because of all those OH groups. So the solubility of alcohols is pretty soluble up to about 4 or so carbons. Then it really starts to decrease. In addition, when we talk about alcohols, they pretty much have really high boiling points and melting points. And that is because they are able to hydrogen bond with themselves. Because they can hydrogen bond with themselves, it makes these really strong bonds and takes a lot more energy to break them apart from each other. Thus, that incorporates to high boiling point. So in terms of winners, in terms of boiling points and melting points, it's your alcohol right over here at pretty high melting and boiling points. So melting points and boiling points, you're going to have high on alcohol. On the other end, you're going to have like your alkanes, your hydrocarbons, your alkenes. They're going to be at the low end of this. And ethers would be, you know, somewhere at this point, a little bit better than alkanes and alkenes and hydrocarbons, but nowhere near an alcohol. So there's actually only one thing that could kind of beat an alcohol in terms of boiling points and melting points, which we'll talk about later on. And that actually is a carboxylic acid. It actually is one of the few things that can actually beat out an alcohol in terms of that. Any questions on that there? All right. Our phenols, which we saw, were basically these alcohols that have the benzene ring on it. They are going to be slightly soluble in water because they have the benzene ring, so that kind of hurts a little bit. They react with water to produce phenoxide ions. They really will do sort of a acid base reaction where this guy is basically just gonna pop off an H plus over there, kind of like the Bronsted-Lowry definition that we talked about when we did acid and bases, and we get this ion that is produced here that lost the hydrogen in this case. All right, so take a second for each of these, decide whether they should be soluble in water or not. OH groups. So there should be some interaction it could do with water. So really what we want to look at is, you know, how big is that nonpolar part of these alcohols? That nonpolar part is the carbon hydrogen part here. And in this particular case, I got 1, 2, 3, 4, 5, 6 carbons, which means that's going to probably be insoluble. Again, it just gets a little bit too big for it to interact well with water. Same idea here. In this case, though, we only have a couple of carbons, and that's definitely under our 5 sort of cutoff. And that then should mean this guy should be pretty soluble in water in this particular case. So again, just because a compound does have a group that will interact well with water, there sometimes are other factors you have to look at to determine if they will interact well with water. And in this case, the kind of nonpolar side is really important. So far on what we've been talking about. All right, so we hit ethers, thiols, alcohols. Feel like I missed something there, maybe not. Might as well continue on. I feel like there's some more to go. We got aldehydes and ketones next. We're going to talk about. We actually talked about how to make each of these. A reminder that an aldehyde has a functional group of carbon, oxygen, double bond, and a hydrogen. That is the functional group of an aldehyde. That is how you recognize it. And for a ketone, you do need a 3-pack of carbons together. And in the center carbon should be a carbon oxygen double bond. So again, that is how you recognize these guys. As we just talked about with our alcohols, we can make each of these based on the oxidation of an alcohol. So again, a reminder that if we had a primary alcohol, we can oxidize this guy and then get rid of these two hydrogens, and that's going to create our aldehyde group here. So again, that is how we get there from a primary alcohol gets oxidized. That is how we create an aldehyde. We can create a ketone through the oxidation of our secondary alcohol. And if we have a secondary alcohol such as this guy here, again, we can oxidize it, removing our hydrogens and inserting our double bond there. And not a weird line that just came there that shouldn't be there. Let's get rid of our eraser here. Get rid of that guy. There you go. And obviously we have that right there, which is our ketone. So again, those oxidation of those alcohols is how we create each of these guys. And they both really do have, as you can see here, this carbon oxygen double bond. And that carbon oxygen double bond is what is known as a carbonyl group. And a carbonyl group, or a carbonyl carbon is sometimes referred to, is a fancy way of saying the carbon oxygen double bond, basically. Now, this group also is important actually in a lot of mechanisms of how reactions occur. And it is a polar group. If we look at carbon and oxygen on the periodic table, they are in the same row, which means oxygen is more electronegative than carbon. And it actually is a polar bond. And the oxygen here will be more negative, and the carbon here will actually be more positive in this bond. And that's actually important in terms of, for example, how certain reactions basically occur. So this sort of polar bond is present both in aldehydes and ketones. Now, there is sort of a difference as well in terms of the aldehyde and the ketone. And when we do see the aldehyde group, because it has a hydrogen at the end, and as we know from our endless conversations about hydrogen, it should only have 2 electrons, 1 bond. It means that that aldehyde group you will always find at the end of a molecule. It can never be in the middle of a molecule. Otherwise, that hydrogen will have too many bonds. So that functional group for an aldehyde will be at one end or the other of the molecule. And that's what keeps basically that hydrogen from obviously having too many bonds. Now, that's actually different than where you would find, for example, the carbonyl group on a ketone. Because in a ketone, you do need a 3-carbon run. The carbon oxygen double bond can never be at the end because you need those 3 carbons to do it. So it actually has to always be kind of inside, and the aldehyde group should always be sort of at the end of the molecule. So again, obviously the ketone doesn't have that hydrogen, and that's what allows it to kind of be interior, if you will. And the aldehyde does have that hydrogen, which means it's always got to be at the end. Any questions on that there? Now, when we draw aldehydes or ketones, we could draw it just like we normally do. If you got, I would say even in condensed form, most of the time people will still sort of draw out that functional part of it. If you really did want to shorthand it, that is actually the shorthand there for the aldehyde group. So this group right here, if you see, I don't use it that often. I don't remember. It is CHO there. That represents that group there that I box. And again, you could do that, but I personally usually will draw it out, and you might want to do it as well. It kind of helps visualize what's going on. For our line structure, it would look something like this. You would do like a double bond. And in this case, it is really important to actually write the hydrogen, because if I did not actually write the hydrogen, what's at the end here? That would be a carbon, which actually would make it a ketone, not an aldehyde. Yeah. So in the case, if you're doing line structure, you do need to make sure that you do include the hydrogen at the end there, to indicate that, again, it's not really a carbon at the end there, that it is a hydrogen. In terms of ketones, as you can imagine, same deal. You'll just kind of draw it in for most people, and you'll have something that looks like this. Because of that double bond, you will get no hydrogens in the middle. Again, sometimes books will use this more condensed formula where they just write a C and an O. And again, that C and the O is basically this part right there, that carbonyl group. So I personally am more of a fan of sort of drawing it out. But again, in books, sometimes they'll kind of use that little shorthand there to indicate it. In terms of line structure, same deal. You just do this and you do that. And that's a ketone right there, right? Because we got a carbon there, a carbon there, and a carbon there with an O double bonded there, right? So again, that's our 3-carbon run with the double bonded oxygen in the middle. Any questions on that? So let's talk about naming aldehydes. Aldehydes is maybe one of the few organic groups where the name doesn't really follow per se. We actually name them with AL at the end of it. So very similar to alcohols, and not to be confused with alcohols, we use AL for aldehydes at the end of it. And it is still basically off of the 10 carbons there are alkanes. So if I had something like this, right? We would count the longest carbon chain, which clearly does need to contain the aldehyde group, 1, 2, 3. And that is based off of propane. This would be propanal, Al at the end of it. Do I need to give the location where the carbon-oxygen double bond is located? The answer is no for aldehydes, because as we just mentioned, it always should be where? To always be at the end. Now, with that being said, even though we don't need to give the location where the carbon-oxygen double bond is in the aldehyde, it is also going to always be carbon number 1 in terms of numbering. So if you had to number this, there is no left or right in this deal. It has to start numbering at that carbon-oxygen double bond. So that has to be the lowest number. And that's important. For example, if I had something else attached there, like this, maybe like that. This now would be still 1, 2, 3 carbons, right? And we have our aldehyde group here. That is going to be still our propanal. But we also have a chlorine group there, right? So we have to give the number of that. Because of this, this guy has to be carbon number 1. This then would have to be carbon number 2. This would be 2-chloral propanal, okay? And that is how we number it. So wherever the carbon-oxygen double bond is for the aldehyde, be it the left-hand side, right-hand side, if there are other groups attached, that's always going to be where you start carbon number 1. And then obviously everybody else would be numbered accordingly. Any questions on that? Some of an old school way of naming, a common way, a reminder that when it says IUPAC, that's kind of like the formal, strict way of naming things. Some common names actually do just use aldehyde at the end of it. And maybe you're familiar with formaldehyde. That would be 1 carbon guy that looks something like this, perhaps. Yeah, that is formaldehyde. By the way, if I didn't use formaldehyde, that has how many carbons? 1, and that's based off of methane. That would be methanal, Al, right? So that is the IUPAC way of naming it. Again, common name is known as formaldehyde. Acetaldehyde, propanaldehyde, and Butylaldehyde here basically is our common way of naming. We are going to go in this class with the IUPAC way of naming, which is the AL at the end of it. I would say maybe the only one you should be familiar with is formaldehyde. It's still obviously used a lot in biology and stuff like that, right? So you should be familiar with what that is. And that again is basically methanol, which is this guy right here. Yeah. Any questions on that there? But everybody else, even with formaldehyde, I would still roll with the IUPAC way of naming. Yeah. So again, we can see our methanol, ethanol, propanol, and butanol. Again, all based off of how many carbons we got going on. All right, so why don't you give the name of this guy? Why don't you give the name of that guy? Why don't you draw 3-methyl pentanal? Why don't you draw 4-bromo 2-ethyl hexanal. We'll hope for the best. Got to turn out to be something, I would imagine. Okay, let's take a look. We'll start with the original one here. First off, this is an aldehyde because that is our aldehyde group. So we're obviously looking for the longest chain that contains that. And in this case, it does look like the straightest chain here is going to do that. So that's going to be 1, 2, 3, 4, 5. So 5 carbons is based off of pentane. It has an aldehyde group on it, so pentanal, Al at the end of it. We do then also have a methyl group hanging out. Remember here, we don't need to give the location, but in terms of numbering, that carbon-oxygen double bond will definitely be carbon number 1, which means that carbon number 2 is where we do see our methyl group. So this would then be 2-methyl pentanal. Any questions on that one there? Coming out over here, this right here is our aldehyde group in sort of line structure form. So we're just going to count our longest carbons. I'm just going to put dots there. 1, 2, 3, 4, 5, and 6. You could also get 6 if you kind of went up that way as well. But 6 looks like a winner here. I'm going to take kind of the straight 6 here. So 6 with the aldehyde group is going to get us to hexanal, Al. Again, in this case, we don't need to give the location of that carbonyl group, but for numbering purposes, that will be carbon number 1 for sure in this case. 2, 3, 4, 5, and 6. So that means that carbon number 3, we have a bromine, right? So we got a 3-bromol happening. And at carbon number 5, we have a lonely line, which we know is a methyl group. So we got a 5-methyl. Just like before, we're going to go alphabetical on this. So bromol first. So this is going to be a 3-bromol 5-methyl as I try to squeeze it in there. Hexanal. Yeah. Any questions on those two names? Yeah. It does for aldehydes. Because that's the functional group, that will always be at the end. And because we always want to always give the functional group the smallest number, that will always be carbon number 1 in this case, because wherever side is it. And again, even though I kind of drew most of them here today on the right-hand side, It could also be that group on the left-hand side, and then you would number left to right in that case. Other questions? All right, then we're going to draw. So just like normal, we're going to draw backwards. Sure what that means, but we're going to draw backwards in the name. So we're going to go Al on that, which tells us it's an aldehyde group, right? So we got to have that. And penta now means that we have 5 carbons. So just like normal, I'm just going to start with the carbon. So 1, 2, 3, 4, and 5. Once again, because you're drawing, you could put the aldehyde group either on the left-hand side or the right-hand side. It doesn't matter. I seem to be going right today, so we'll just do everything over there. We'll put the group over here. And that is our aldehyde group at this point. That takes care of this. As we just talked about, because I did put my group there to the right, for me, that has to be carbon number 1. Now, if you put the group over here on the left, your left carbon would be carbon number 1 for you in that particular case. We're going to go 3 places over and put a methyl group, which is a 1 carbon group right about there. And now we're just down to hydrogens like normal. So a couple of hydrogens there, 1 hydrogen there. How about 3 there, a couple there. Why not 3 there? It looks good. Any questions on that one there? Yeah, so again, I've been drawing condensed. It didn't really specify you could draw anything. Again, if you're going to do the line structure, you would do basically the same thing. You would start with your carbon. So you would have, before you change the page, you would have your 5 carbons, 1, 2, 3, 4, 5. And again, here we do want to make sure that we put our aldehyde group there. And again, you could put the H like that. And that would be carbon number 1 here. And here we could then, what we got there, 3, right? So 1, 2, 3, we could do a methyl group. Or if you wanted to make it look a little bit prettier than that, you could kind of do, if I could think about it here, do that, and not have that extra line there, which would make 6, but you could kind of do it that way as well. That's going to erase everything. So there you go. Try that again. So you could, kind of do this part here and then make your double bond and go, that's carbon 1, 2, 3, 4, and 5, something like that. And then 1, 2, and 3, go like something like that. Either way is perfectly fine. Yeah. Question on that one there? All right, hexanal, same thing. I'm going to start with ALs, our aldehyde group, 6 carbons, 1, 2, 3, 4, 5, and 6. And just to mix it up here, I'll go my aldehyde group on this side. And again, you could put it obviously on the right-hand side like I've been doing. That means for me, because I did put it over there on the left, that's going to be for me carbon number 1 this time. That means at carbon number 2, I actually have a 2 carbon group, which is my ethyl group. And at carbon number 4, I have a bromine, basically. And now we're ready for hydrogens. So we could add our hydrogens there, 2 there. This guy only needs 1. This needs 2. This guy needs 1. This guy needs 2 and 3. And that is it, I think. Yeah. Any questions on aldehydes, naming, drawing? Okay. All right, then let's take a look then at some ketones, I think. Let's talk about naming ketones. So ketones are a little bit different. We do drop the E off of the alkane name. And because ketones ends in ONE, that is how a ketone ends in ONE, basically. So we are going to give the longest carbon chain that has that ketone group. So here we have 1, 2, and 3. That is going to be propanone. By the way, propanone is the smallest ketone you could have because you need 3 carbons in a row, right? So because of that, that's as small as you could get in terms of a ketone. Here we have 1, 2, 3, 4 carbons. That's butanone. O-N-E. Now, when we actually do get to, with ketones, 5 or more carbons, there are multiple places where that OH group can end up. Not the OH group, where the carbon-oxygen, carbonyl carbon can end up. And because of that, we then now need to go back to given the location of where the carbon-oxygen double bond is. So with aldehydes, we don't really need to do that. With up to 4 carbons, we don't really need to do that. You may be asking, don't you need to maybe do that with this guy? Well, if I drew it like that, my other option would be to draw it like this. If I were to number where that carbon-oxygen double bond is in the top one, what carbon should it be at? Carbon number 2, yeah, the smallest number. Now, if I drew this one and I want to number that carbon-oxygen double bond, what number would you end up with? You would still end up with 2 because you want to give it the smallest. So there is no difference here. But when we get to 5, there is a difference. So for example, 1, 2, 3, 4, 5. If I have one there and I have one there, where is the carbon-oxygen double bond in this one? Which carbon should it be? 2, right? Smallest number. How about this one? It is 3. 1, 2, and 3 are 1, 2, and 3, no matter which way you go, right? So there are differences. One would be 2 and one would be 3. So 5 or more carbons with a ketone, you do have to sort of insert the number of where the carbon-oxygen double bond's located, just like we did with double bonds, triple bonds, OHs, and all those type of things. That's where this sort of starts. So that's how we get down here. 1, 2, 3, 4, 5. That is pentanone, O-N-E. The double bonded carbon oxygen, 1, 2, and 3. It really is 1, 2, and 3, no matter which way you go. That's going to be our 3-pentanone. By the way, what would this one be called then? 2-pentanone, right? So it still has 5 carbons. 1, 2, 3, 4, and 5. So that is also pentanone. But our carbon-oxygen double bond, which is right here, is at carbon number 2. So it's right there at that 5 carbons. So you do have a couple of options as to where that can be. So really, as you probably can tell, organic naming is all about just telling people where things are, right? So you have to give the location. We could also have ring type ketones here, as you can see. And in this particular case, it's just in case you can't see it, this right about here, that is a carbon, carbon, carbon with a oxygen double bond in the middle. So that is actually a ketone that is hanging out there. The main part, though, is the ring. And that ring is a 6-member ring, which is based off of cyclohexane. And this then becomes cyclohexanone. Now, in this particular case, because it is a ring, we actually do not need to give the location of where the carbon-oxygen double bond is. But as you might be able to guess, that carbon-oxygen double bond should be carbon number 1. Yeah. So that should be carbon number 1 for something like this, where we do have a second group off of there. And that would give us 1, 2, and 3. And that's how you can see down here, they get to 3-methyl cyclohexanone in this particular case. Question on that one. So in a ring structure, you don't need to give the location, but it will be carbon number 1 where that carbonyl carbon is. And that's for numbering any other groups that may be attached. Question. All right, so why don't you name that one? Why don't you name this one? Why don't you name that one? And why don't you draw? Let's try this here. Let me draw Let's go with 4-methyl 2-hexanone. And why don't you draw Okay, let's take a look. We'll start with the original one there. Hopefully you can recognize this is a 3-carbon run with a carbon oxygen double bond in the middle. So that's going to tell you we're dealing here obviously with a ketone. So we obviously want our longest carbon chain to contain that. And there's a couple different ways you could get it, but we might as well just go straight across. You could also get it by going down to that methyl group there on the bottom if you wanted to. That is 1, 2, 3, 4, 5. So that's going to give us a pentanone, right? Because it's a ketone. Because it is definitely 5 or more carbons, we do need to give the location of where this guy is at. And again, we want to give that functional group the smallest number always, pretty much in organic. You could probably see if you go right to left here, that is going to achieve the smaller number there for that. And that would then mean that this is 2-pentanone. At this point, because we're locked into the numbering going in that direction, that would mean that my methyl group would be at 4, and this would be 4-methyl 2-pentanone. Any questions on that one there? Where to go next? We'll go up here. So hopefully you can see right here, carbon, carbon, carbon with a double bonded carbon there at the top. So that is, again, your kind of ketone group coming through that way, basically. This is obviously part of a ring, which actually has 5 carbons on it, right? 1, 2, 3, 4, and 5. So that's going to be based off of cyclopentane. And that's going to give me cyclopentanone in this case. Here we again do not need to give the location of that carbon oxygen double bond, but because we obviously do have another group attached, the importance of that is where that carbon oxygen double bond should be carbon number 1 in this case. Just like normal, we still want to give that group the smallest number. So going kind of counterclockwise here will allow you to do that and get to 2. Obviously, if you went in the other direction, you're going to get a much bigger number going that way. So putting that together, that's going to be a 2-bromol cyclopentanone. Any questions on that one there? All right, one on the bottom there, in the middle, I guess. Carbon, 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 3-carbon run with the carbon oxygen double bond in the middle. So that is our ketone hanging out right there. Again, we're going to look for the longest carbon chain. I think in this case, we're just going to straight across. So 1, 2, 3, 4, 5, 6, and 7. If you actually went down, I think you only get 6 carbons. So once again, 7 looks like a winner there. 1, 2, 3, 4, 5, 6, 7. That's going to be a heptanone. Here we do need to give the carbon oxygen a number. So if we number left to right, 1, 2, 3, 4, 5, 6, 7. We'll do it a different color going in the other direction here. We'll go this way. If we go this way, 1, 2, 3, 4, 5, 6, and 7. Now, in the case of the carbon oxygen double bond, does it make a difference? It doesn't. It's a 4 no matter which way you go, so might as well throw that into our name. But now we do have a couple of groups attached here and here. Does the group numbering make a difference depending on which way you go? It does. And which way would we want to go? We would want to go with the red direction in this case, right? Left to right. That's going to give our groups, which would then be kind of the next important thing, the smaller numbers. So that means we would have a 2-chloral, right? And that little line there would be a 3-methyl. Again, we want to go alphabetical orders. So let's go above it one more time here. 2-chloral, 3-methyl, 4-heptanone. That is a mouthful. Guess that's what you get when you just draw lines, I suppose. Any questions on that name there? Yeah. All right. Now we're gonna draw some stuff. I will do the long one first, I suppose. All right. So let's go with actually I'm gonna clear up some room up towards the top to do that one, I think. All right. So obviously we're gonna go backwards here. So we do see ONE, which tells us it's a ketone. We see hexane, basically, which tells us it's 6 carbons. So we just want to do our 6. 1, 2, 3, 4, 5, and 6. The 2 tells us that is where the carbon-oxygen double bond should be located. And again, since you are drawing, you could go left to right or right to left. I'm going to put mine right here, and that's going to be carbon number 2 for me. Obviously, if you did it this way, that would be carbon number 2 if you went that way. Because I went that way for my carbon number 2, that means 2 doors down there should be a methyl group, right? Which is a 1-carbon group. At this point, we're now down to just hydrogens. So we're going to go 3 there, 2 there, 1 there, 2 there, none there, right? Because it's got 4 bonds, and 3 there. Again, if you want to do some type of line structure, same deal. You want to start with your, what we got there, 6, right? That I could maybe squeeze. We'll go right here. 1, 2, 3, 4, 5, and 6. And again, we would do a double bond and then a line. Yeah, it would be something like that. Any questions on either of those there? All right, cyclopropanone. So ONE tells me it's a ketone, propane tells me it's 3, and cyclo tells me it's a ring, right? So that is a fancy way of drawing a triangle, I suppose. Yes. And onto that triangle, though, we do need the carbon-oxygen double bond, and it doesn't really matter where you want to put it. I'm going to go this way because I'm running out of room going top wise, so I'm going to put mine there. But you could put it on the top, you could put it to the left. It really doesn't matter in this particular case. Any questions on how to name or draw ketones? So let's talk a little bit about aldehydes and ketones and water in terms of solubility. They can form hydrogen bonds with water molecules between the carbonyl group and the hydrogen bond and water. So as I mentioned a while ago, this group here is a polar group, and water itself can actually hydrogen bond through its positive hydrogen there. And that's going to make it pretty soluble. They are very soluble in water because they have the ability to do that. Also, the ketone can also do that as well. But again, it does have to do with the amount of carbon chain that we have. So if we have 4 or fewer carbons, they will be pretty soluble. But if you have a much longer carbon chain, you're going to kind of see, like we saw with the alcohols, basically the solubility drop basically to nothing. So that's what this sort of chart sees. Upwards of like 4 carbons, you're good to go with water. It's going to be soluble. But again, once you kind of get over that 5-ish, which kind of like a lot of organic is kind of the limit there, kind of get 5 or more, you start to really see things becoming slightly soluble, which is almost insoluble. And then as you get to obviously 6 or more, you're going to get into things being insoluble. So again, that kind of buildup of the non-polar part can really affect obviously the solubility that we see in water. All right. Any questions on that there? All right, we're going to lay it up there